Welcome to the first session on supernovae. Today, to tell us a bit about everything about supernovae, core collapse supernovae, not 1As. It's Dave Sand on his talk on the core collapse supernova landscape, infrastructures, and science opportunities.
Thank you, everyone. I'm so glad to be here. I hope I am not too loud. I feel too loud. I always feel too loud, but now especially so. Okay. I was asked to talk about core collapse supernova. I kind of want to make sure this works. Oh, yeah, it does. So I have to point at this. I will get there, I promise. I was asked to talk about core collapse supernova and kind of the landscape in terms of infrastructure and science opportunities in the coming years. And I was like, why core collapse supernova? So like I immediately crossed it out. I'm sorry, Ryan. I don't know why. Okay, I don't even think of myself as a core collapse supernova guy, but okay. So the point is we live in this really rich landscape now, and in the very near future, it's going to get even richer. Obviously, LSST, we're right on the doorstep. Your favorite surveys are here, depending on who you are. I'm looking at all of you in this room, okay? On the horizon, things like, well, Roman, of course, Ultrasat, UVEX. I will touch on all of these at some level, but it's just to say that it's such a wonderful time to be us right now. And it really is a fun kind of journey that we're all going through. Okay, so I have two summary slides. So I know it's early in the morning on the last day. I will show you two quick things that I hope you take away. And then the rest you could kind of be like, whatever. Okay, so we live in this landscape now. I just showed you this awesome landscape where we have many surveys. And we've heard a lot of this from tests plus surveys, ZTF, combining with Atlas, all of this stuff. We could combine all these surveys now. And I would argue we can even combine bigger glass now with LSST to really study young transients from their very earliest moments. And I want to show just this example. This is Wynn's favorite transient from his toast the other night, 23 IXF. And of course, I'm going to keep screwing this up, of course. Yeah, I'm sorry. You know, when I teach a class, I just use the button on the keyboard usually. Now you know why. Okay, so here's 23 IXF. I could literally point. And what we noticed, here's the wonderful early ZTF data point, but because it was in M101, every university telescope, every amateur astronomer was actually observing M101 like every night, just like they all do, okay? And so there is this rich set of early time data that you could see there, that little uptick, that excess in the early light curve in comparison to data points later on. That's something we really haven't seen before because it's extremely faint. It's in this regime of -13, -12, -11 absolute magnitudes, where most surveys don't probe, okay? Now, if you look at LSST, LSST can do this out to 200 megaparsecs. There are many dozens of type 2 supernovae every year within 200 megaparsecs. Okay, where you could, in principle, capture this kind of early light curve feature. Okay, now if you were shadowing LSST with something like DECAMP, okay, you can't do the whole sky, you could do parts of it, right? Then let's say you go a little bit shallower with DECAMP, then you could do it to say about 100 megaparsecs. Still, there are many type 2 supernova every year within 100 megaparsecs in order to capture these very early light curve features, okay? Okay, so that's takeaway one. And I do just want to say, because this is a Roman conference, I do think it's important. We talked a lot about collecting lots of light curves in the HLTDS. We want to study, there's this whole, I was so excited by the talk yesterday about gap transients. There's this whole regime of transients that we might miss out on if there isn't some kind of targeted thing. You could even plan it to do other types of science. I'll stop right there. I love dwarf galaxies. I will keep going. All right. All right, so it's alert time with LSST. There are millions of alerts. the theme coming up over and over again in this conference and for the last 10 years is what are we going to do with them all? I guess we haven't quite figured it out yet, okay? I think us as a team, nearby supernova people have a pretty clear idea of what we're going to do with these alerts. It's pretty easy to filter on nearby galaxies, and any little blip in a nearby galaxy, we can really go after them, okay? I stole this slide from Igor and Armin a couple conferences ago, okay? So they get full credit for this. This is just kind of the follow-up landscape, just to give you an idea, okay? From 1 to 2 meter class spectroscopic follow-up, okay? Here, people love SEDM. I love Floyd's forever, okay? There are great follow-up facilities at that level, all the way up. SOAR is certainly going to become an important follow-up facility in the LSST era. SOX, we're not European, they won't let us in, okay? Going all the way up, okay? Here's just the photometric version of that. Okay, now I'm going to give you my science philosophy slide, and most of the people in the room won't agree with me, but I actually think it's good. We've heard a lot about gathering large samples of data, maybe even just light curve data. I want us to think a minute about what we could do with LSST and other facilities, especially when we combine them, about getting the dopest data, the most awesome data of individual supernova, okay? Because I would argue getting the greatest data on nearby supernova is what we want. It's what drives the models. It's what drives it. It teaches us new observables. I just showed you that early light curve excess in 23 IXF. We could not see that in a poorly sampled light curve, even 10,000 of them, okay? So samples are great, but I also want you to think about getting the greatest data sets on nearby supernova, because it will drive the field all the way down to the base of the pyramid, so that others can get statistical data of the one awesome thing that you found later on, okay? All right, so we tried to do this. This is just kind of a pathfinder project you could think of. The DLT-40 survey is the supernova survey none of you have ever heard of, except for the people who work on it, okay? So there are all these early signatures in young nearby supernovae that teach us about what type of star exploded and how it exploded. You could list them over there in a table. This is what we do. We plop it in our proposals, okay? They can be seen in certain absolute magnitude ranges, okay? And they have certain time scales, and they're all hours to days, okay? And the thing I want you to keep in the back of your mind is that the Wide Fast Deep survey has a 3-day cadence. So you miss all of these, okay? So you have to think about what you're going to add to that if you want to get these really great data sets in the LSST era and get even more examples of them, okay? And of course, this is my beautiful IDL plot from 10 years ago now, okay? So don't judge it, but it's kind of an early version of, you put down the absolute magnitude of all of these early light curve signatures, okay? We have a 16-inch telescope. It could go down to 19th magnitude in 45 seconds or whatever, okay? All right. That is 19th magnitude as a function of distance, okay? And you just draw a line down, 40 megaparsecs is out to which you could observe these early light curve signatures. It's that simple. That's why it's DLT-40, okay? Yeah, it's that simple. I'm a pretty simple guy. Okay. All right, so here is the idea in a nutshell. We use small telescopes in Chile, Australia, Canada. We're actually putting one in right now in Arizona. We're not going to stop, okay? We love it too much. And, we observe nearby galaxies within 40 megaparsecs every night. Every damn night is what I tell people, okay? Sometimes every 12 hours, okay? Because we do not want to find a lot of supernova. We just want to find the really great ones very young. And in fact, we don't even care if we find them. We want Atlas to find them and us to have a non-detection 12 hours before. We really don't care, okay? We just want to find them young and trigger all of these facilities in order to get the greatest data on these nearby supernova. We heard a really great talk from Nabil yesterday about all the software and technology that could go into automating or nearly automating these kind of searches. I think that's really great. We have our own version of that. I don't need to go over it because Nabil covered it better yesterday. But we are able within 15 minutes to trigger spectra on Floyd's, which is the 2-meter spectrographs on Fox Telescope North and Fox Telescope South. The thing that we are able to do, this came up a little bit yesterday, is, DLT-40 is not doing anything better, okay? So if we find something with a high ML score in the middle of the night, we drop everything and we go observe it for the rest of the night, okay? So this lets us, so first we get a confirmation image, so high ML score. Okay, let's go back, get another image. If it has another high ML score, we keep going. Now we do multi-band and we just don't stop, okay? That lets us get light curves like this. This is a color curve of 24 GGI. This is like the paired to 23 IXF. When I see a color curve like this in a light curve modeling paper, I thought, hey, these simulators, their code didn't converge. There's something wrong. But no, this is a real observation of within hours, well within a day, the light curve, the color of the supernova changing in real time. This is some kind of shock breakout cooling through a CSM envelope, something like that, okay? I'll stop talking about infrastructure a little bit, but we've enabled same night triggering with the MMT, with our TOM. We'll hear more about our TOM, the Saguaro TOM later from Vagya. Okay, so I already hinted at this. That's the DLT-40 survey. We need to think a little bit ahead to, it's too late. LSST has started, okay? So we need to think now about LSST and how to catch these things very young. And I just want to emphasize that the wide fast deep with its 3-day cadence isn't great for this, but we can still do it. Okay, I'm going to talk a little bit about the actual science and motivate it a little bit more. I promised I'd talk about thermonuclear supernova too, sorry. Okay, so type 1a supernovae, their early light curves can give you some idea of the progenitor system. Imagine 2 white dwarfs or a white dwarf with a normal companion star, okay, feeding the white dwarf. In that case, the explosion may run into the non-degenerate star and create an early light curve excess. This is an old prediction from Dan Kaysen for that. You'll notice that it's only within the first couple days that we expect to see such a signature. There are actually other predictions for the very early light curves of type 1a supernovae. There's a whole zoo of features you expect to see, whether it's from nickel clumps or CSM interaction plus nickel clumps, or you could create all kinds of things in the first couple of days that teach you something about the progenitor system, okay? And it's been nearly a decade now since 2017 CBV and supernova like that, where we are seeing these early light curve excesses within the first couple days of explosion. You see it's stronger in the U band and in SWIFT than it is in the red bands, kind of like the prediction. I'm not saying we've confirmed the prediction at all. Actually, it's quite problematic, okay, that we can't quite match all the models. But you'll see we're getting samples of data like this now. And this is just another example of DLT-40 just dropping everything and just observing over and over and over again these fields. Okay. Here's one example. This is from Griffin's paper in 2022 of 21 AEFX. This is us modeling the early light curve of 21 AEFX as if it was the shock companion scenario where the ejecta runs into the normal companion star. You expect this early light curve excess, and we can model it in the optical in a decent way. But if you then take it to the UV and say, okay, what if that shock was real in the optical, what will we see in the UV? This is the prediction here, the shock only prediction, and it does not match the early UV data. Okay, there's a good mystery here, we like that. Also, this very early data of 21 AEFX the very early spectrum that we got from SALT, we discovered these things in Chile or Australia, and then we were like, hey, Saurabh, help us out, homie, okay? And he takes a spectrum for us a couple hours later. Beautiful data. This type 1a, its earliest spectrum had a velocity of 30,000 kilometers per second, 10% the speed of light, okay? Never, again, another thing never seen before in a type 1a supernova. The next day, it's down by 8 or 9 1,000 kilometers per second. Sorry. 8 or 9 kilometers, even almost I could do. Okay, so you can see the spectrum is very blue shifted and it quickly shifts over, okay? You can see in that sequence. Again, this is something we don't understand. We've seen it in a couple of systems now, this early light curve excess in conjunction with high velocities at the earliest time that quickly step down. We're not sure what's going on. Actually, we have one now that did not have a very high velocity, which is a bit of a mystery. And of course, when you study these very early type 1As very nearby, they're actually prime targets for things like JWST. JWST hasn't been talked about a lot today, or at the whole meeting, but there you go. All right, I'll move on to core collapse supernovae. We heard a bit about flash spectroscopy yesterday. This is probably either some kind of shock breakout or ejecta interaction with circumstellar material just outside of the red supergiant star at the time of explosion. So it's teaching us about the environment of the progenitor star, okay? You could see in the first couple of days, you see these high ionization lines in the spectrum that disappear, okay? This has been seen for a long time, but was re-highlighted by Avishai back in 2014. I also want to pair this with 23IXF and this early kind of amateur light curve that we were able to put together to see this excess, okay? Maybe these two are related. The CSM is causing this early light curve bump and the flash spectroscopy that we see. And I do want to point out that if you were shadowing LSST with DECAM or something like that, you could have seen this signature out to 80 megaparsecs or so. So instead of the nearest supernova in a decade or whatever you want to call it, we could be seeing this every couple weeks, okay? I also think it's important to get intensive spectroscopic cadences. I'm still waiting for the paper that takes all of the flash spectroscopy from 23XF from every group and brings it together in one formal analysis. I know we took 3 or 4 spectrum per night at some point, and we were seeing evolution in the same night, okay? So it is sometimes worth getting spectra the same night of the same object. I'll show a couple examples of this later. Here, I won't belabor 24 GGI. This is kind of the cousin or the sister or the brother of 23IXF, also at 7 megaparsecs, also an incredible data set. It lets us compare 2 normal type 2 supernova from the earliest times, okay? And in particular, we could compare the flash sequences between the two, okay? We see that for 23IXF, these flash features lasted for several days longer than they did for 24 GGI. You know, at the most basic level, that indicates that this dense CSM was more extended around 23IXF than it was for 24 GGI. So type 2 supernovae or the red supergiant environment around them is not the same from supernova to supernova, okay? They're still exciting. I'm messing with you. We've started to move from just taking normal, let's say R to 500, R of 500 to R of 1,000 spectra of these nearby supernova to just doing high resolution spectra if we can, if they're bright enough and near enough. Here's one example for 24 GGI. This is with Mike down at Las Campanas at Magellan. I love telling the story where Griffin asked the observer, hey, can we get a Mike spectrum of this object? No, actually, we're like, hey, we should ask for a spectrum. And Griffin's like, let's ask for 2 spectra in the same night. I'm like, Griffin, that's too much. You can't ask for 2 spectra in the same night. But he did it anyways, and I was wrong. And he was right, and we got an amazing data set. It evolved over 8 hours, okay, very clearly from epoch 1 to epoch 2. You can see in the black to the red. There's also this little divot here, this mini P Cygni, 40 kilometers per second. We think we're probing the red supergiant wind just prior to explosion. Okay, so we could learn about red supergiants just before they exploded by studying early supernovae. Okay. Okay, I got one more really cool high-res spectra that I really have to show you. I know I only have 5 minutes. Okay, we have a large and long program with Gemini that not only takes normal optical spectra, normal near-infrared spectra, but we take high-resolution spectra multiple times on these supernovae. Early on, this is 25 NGS, it was one of these flash spectroscopy type 2 supernovae. Our first Maroon X, normally used for exoplanet finding, our first spectrum, that's H alpha. You see that double horn profile? Even I know, I teach grad galaxies what a double horn profile means. Some kind of disk, okay? Some kind of CSM disk around the red supergiant prior to explosion that we're probing here. The ejecta's running into it, okay? That feature is about, let's call it 30 kilometers per second in size, okay? Next day it was gone, by the way. I will skip these because I'm running out of time. I was just so excited about the test stuff that I want to show our stuff. You could ask me afterwards. So I did want to highlight a couple of community programs in this era of LSST where we're trying to bring together resources from multiple telescope facilities at the same time to study these young nearby supernovae very intensely. The pitch I'm trying to give you today, the pinnacle of the pyramid, okay? Griffin is leading this PASTA project, Public Aeon Spectroscopic Survey for Transient Astronomy. It's a long-term project with SOAR that everyone is welcome to join. We look at supernova within 50 megaparsecs that are discovered young. We get optical near-infrared spectra, both early times, a sequence, and at late times. All of our spectra are public. We put them on WISE-RIP and TNS within 24 hours. Please use them for your proposals, even if you're not on the team, but you should be on the team. Okay, so we could not do this if we weren't part of the Global Supernova Project at Las Cumbres Observatory. Las Cumbres has 1 meter telescopes all over the globe, along with a pair of 2 meter telescopes where they have spectroscopy as well. This lets us get those intense early light curves. They're really just hard to do otherwise. We just pass from one telescope to the other for a given night for days on end, okay, to get these really, really great light curves from nearby supernovae. This is another project that you could join. It's a public project. Please do talk to us. And then finally, I want to talk, I will end, I promise, with this newly approved Noir Lab program to shadow LSST. We've heard, I know ZTF is doing this, LS4 is doing this. We're going to do it with DECCAM. Again, the philosophy is we want to go deeper, find them younger. We don't want to find a lot of them. We won't, okay? But those that we do find are going to be really great, and we'll get on top of them and get these one-of-a-kind data sets again, okay? So the idea is LSST, wide, fast, deep, has a 3-day cadence, night 1, night 4. In between, we will observe with DECCAM in certain select fields. This is an approved program. I don't know why we did this. It's 80 DECCAM nights, but don't think of it that way. It's like 1 or 2 hours per night for forever, okay? So somehow we have to staff these nights. I really hope Aeon works very soon for DECCAM and that we can do this, yes. Rachel, I'm looking at you. Otherwise, we're in trouble. Okay, the idea is that we'll find over the course of this survey 25 supernova, very young, very nearby, that we could get these one-of-a-kind data sets on. Okay, these are our fields. You can talk to me about it afterwards. I'm running out of time. I do just want to highlight, let's dream big, guys, right? We could think about the next few years. I promise I'll be done. What if we shadowed LSST with DECCAM a lot more than we're doing with this program? How many of these early light curves could we capture in a year? Okay, and I'll just flash these up because I'm out of time. You know, normal core collapse supernova, LSST could see that out to 200 megaparsecs or 100 megaparsecs with DECAM, okay? We're talking, okay, just under 100 per year that we could get this kind of data set if we wanted. Type 2Bs, these extended envelopes that have these shock cooling light curve excesses early on, we could be getting 15 of these per year with some kind of shadowing program. I'll skip that for now. And literally hundreds we could be doing with thermonuclear supernova as the screen turns red at me. And so I just want to show some very early data from this program, okay? We are taking data now, even though LSST alerts haven't started. So we're kind of just trying things out, getting our pipeline running. We wouldn't be able to do this without the Carnegie Mellon DECAM difference imaging pipeline, but it's let us get online very quickly, and we're very grateful to our collaborators on this. Here is a luminous blue variable eruption that we just found in the last couple of days. It actually was seen once before in 2017, okay? We'll be able to fill in this gap, you know, the gap between novae and supernovae all throughout our survey as well. Everyone wants me to stop. Just please get excited about LSST and DECAM. I'm 1 minute over. I'm pretty good. All right. Thank you. Thank you.
Thanks, Dave. Well, you heard it here first. Dave claims he can run at 8 kilometers per second. I'd like to see that.
I actually have a story about this, but after, yeah.
I think we have time for like one question. I will take one for someone without a PhD.
I'm really nice, I promise.
Yes. Any questions? Almost. No, I'm waiting. If anyone else. Okay, Ori, go.
Well, you reminded me of RFK Jr. with that pyramid. I'm thinking, you know, I know. So he flipped the pyramid, and now meets are now the base. So I'm just saying, you know, you might want to consider that the high resolution spectra are now the base of all of astronomy. So.
Anything else? No, then let's thank Dave again.